So it's really good to actually know, what we've already done, what we're doing next, and how these ideas fit together. All right, so let's have a little talk about some of the waves that we've already encountered and some of the stuff we're going to be learning about over the coming videos on this channel over the coming weeks. So one thing that we're going to have to do is we're just going to start by looking at really the waves basics. Now, I've covered some of this material already for us, demonstrating that waves transfer energy and not matter. We talked about a wave being a transfer of energy within oscillation. We can go a bit closer into oscillation in terms of our Newtonian mechanics and stuff like that. Describe what is meant by wave motion as is illustrated by vibration in ropes and springs and using experiments using water waves. So different ways of modeling these oscillations and these waves and how they're transferring energy. Wonderful. Use the term wavefront. We're going to have a look at that. We're actually going to have a bit of a deep dive into that to try and get a really good understanding of what's going on there. Give the meaning of some of our waves' fundamental properties. Its speed, which we do already know from forces in motion, just the idea of speed, right? Frequency, how frequent the wave is, measured in hertz. Wavelength, how long the wave is, measured in meters. And amplitude, how tall the wavelength, measured in meters again. Awesome. And we can put some of that information together into that equation, into that wave speed equation. Wave speed equals frequency times wavelength. Wonderful. So if you're recognizing some of these facts so far, and you're like, I know that. I know a fair bit about that. I know 60% of that. Wonderful. You're already in a really good position to be talking about general wave properties. Distinguish our differences between a transverse wave and a longitudinal wave, and be able to give tons of different examples. We'll be looking at that together, of course. And describe how waves can reflect, refract, diffract. I want to add transmit and absorb in there as well, because I think if we're going for real understanding, we should know all of our wave boundary interactions, all the things that can happen to a wave when it encounters a boundary, right? Describe how wavelength and gap sizes affect diffraction through a gap. So, and describe how wavelength affects diffraction at the edge. So how waves change direction and change shape, and wave fronts change as they approach gaps and edges and things like that. So we'll do a few different things to model that to see if that can hopefully stick in our brains, and talk about all those things that we just did with the example of water waves. Now, another wave that we're going to be looking at really closely is we're going to be looking at light, right? And the wave boundary interactions that can happen with light. Yeah, reflection, something we observe all the time. So I don't think that's going to be something that's particularly tricky on a conceptual level to get on our brains, right? So how things like a mirror, can create an optical image, optical meaning light, right? And recall the law that our angle of incidence is exactly the same as our angle of reflection. Things that we see in a plane mirror are virtual. We'll cover the virtual and real images, and we'll do simple construction lines with ray diagrams and stuff like that to show where optical images may appear. Yeah. Now, we talked about reflection of light there, refraction of light. Describe experimental demonstrations of refraction of light, right? So remember refractions when it's slowing down or speeding up, changing speed or direction. Yeah. Use terminology like the angle of incidence and the angle of refraction, and talk about how it's passing through materials there. Wonderful. Give the meaning of critical angle and describe internal reflection and total internal reflection. Yeah, something that's really useful for our fiber optic broadband signal, something that's kind of really important to us right now that we're all trapped inside. And then we're going to use some examples of these refractive indexes, which is basically a number telling you how much something refracts, right? And putting those into equations, right? So I think some of this might be quite new to us, but again, if we work on these building blocks and we go through these sequentially, I don't think it'll be a problem. Also, we're going to be checking out converging lenses, describing how lenses that that converge together, how they affect light, right? How they can affect the focus, the focal length, depending on the thickness that may have. And again, we're going to be using diagrams to draw these situations out, how they can produce real and virtual images. Two terms that are going to be really important, not only for the lenses, but also for the reflection. Okay. and how light actually disperses. Yeah, how light can disperse and split up by some of those, as seen in those original prism experiments by Isaac Newton. So forces, which we've looked at a lot together, energy that we've looked at a lot together. If you can't remember that stuff, please go back. And waves, these are really, really, really big fundamentals of physics. And we'll see how a lot of these ideas actually really meld closely together. Yeah, all the stuff that we're doing in waves, it does have a basis in Newtonian mechanics and Newtonian physics. So that's where we've been, and that's where we're going. So this might give us some confidence in what we already know, and also give us a roadmap of, okay, this is what I'm building towards, and this is how these ideas might connect together. If there's any of these points that you're not sure of right now, or ones you just want to show off that you already know, just comment them, yeah, and then we can check, and I can give you feedback on how we're doing there.